All right, everyone, if you are watching at home, we're going through applications in 3 dimensions. And this is the last exercise that we'll be doing this year. Unit circle will be done in semester 2. So this is the end of your notes. Now, what we can do is really, we're just going to be looking at exactly the same theory, SOHCAHTOA and also potentially Pythagoras theorem, if we need to. And we're going to be looking at things in 3 dimensions, and we've got to be able to draw and label right-angled triangles in 3 dimensions, and also to apply the trig ratios for these problems as well. So we're going to have a look at some things like this. Here's an example of a vertical flagpole supported by 2 wires. Nothing too crazy though. There really isn't. Now, if we have a look, for example, here's a pyramid. Now, this pyramid has, if I was to ask you what would be the height of a pyramid, let's do a square pyramid, something like this, then I might ask you what is the height, or we might be given the height to the what we call apex. This is what we call the apex of the pyramid, the top of a pyramid. Now, if I was to take it from the center, you notice that, yes, this is like a square-based pyramid, something like it's got a square base. And if I'm looking at the center of the pyramid, you notice that I could actually do a few things. I could draw a line across there. I know it looks different because it's in 3 dimensions. You know what? I'm going to make it a red line. Okay, so here's my red line. Now, notice that it's really important. That is exactly perpendicular with this line to the apex of the pyramid. Okay, so that is perpendicular. And also, though, if I look at the face of the pyramid, it's going to look something like this. And there you go. I've just formed a right-angled triangle. Okay, now I could actually do that so many different ways. I could do it like this. Okay, that still forms a right angle triangle, and I could do that so many different ways. And when drawing these, we'll need to then use trig ratios to find out various things. We're better off just getting started with an example. So let's read through this really carefully. Let's get our highlighter out just in case there's anything that we miss. So really important. If I don't take my time, I make mistakes when doing these if I am trying to rush. You can't rush worded questions. A vertical mast, let's have a look. A vertical mast is supported at the top. So this thing here I'm gathering, is our vertical mast because it goes directly up and down. And it's supported by 2 cables reaching from 2 points, A and B. So they go out to A and they go out B. It says that, and thankfully we've been drawn a diagram. You might not be given a diagram. Point A is 36 meters long and is at an angle of 48 degrees to the horizontal. What else could we call that? That would be the angle of elevation. Yeah? So we could also ask for that angle of elevation. Point B likewise is 24 meters from the base of the mast. Okay, we don't know a couple of things there. Now it says here, find the height of the mast. Now the thing is that, by the way, can I just suggest, for a triangle, we know with SOHCAHTOA and any trig ratios, let's just say if I had sine of 27 degrees might be an opposite over hypotenuse. If I know 1, 2 of those things, I can find the third thing. Yeah? You notice in this triangle over here, though, how many things do we know? We know 1 thing, which means that there is no way we could ever use SOHCAHTOA unless we found out 2 things. What do those 2 triangles, which I've drawn, in 3 dimensions, drawn here, what do they both have in common? Would you agree they both have this vertical height in common? So if we did the triangle on the left, I'm going to call that triangle 1. And then, because triangle 1 has an angle and its hypotenuse, which we'll get to in a second. So if we use that, if we know that we've got 2 things, we can always find the third. Then we can apply that for the second triangle, I'm guessing. I haven't even read the question, but I'm guessing that's what it's going to be. A lot of these are very similar. Now, let's just see. It says find the height of the mast. So let's call that H for height. I'm not going to call it X or Y. That wouldn't make much sense. And of course, we've got our triangle in 3D over here. I'm going to draw it dead flat, okay? Yes, in 3 dimensions, it's going to look like it's on an angle, but you know what? There is my 48 degrees and my 36 meters, and there is a height. Okay, so let's do that. Find the height of the mask. Well, we've got, let's label the triangle. Let's label that properly. You need to do that for every triangle. This is adjacent to the angle, isn't it? And this is the opposite of the angle. And we also need to, well, we do know the hypotenuse. Now, we don't know what the adjacent is. Yeah, sure, we could find it later if we wanted to, but what we're concerned about is finding the height. So that means we've got the opposite and the hypotenuse. So you should hopefully identify that what we want is we want sine. Sine of 48 degrees is equal to opposite, which is h, over the hypotenuse, which is 36. Now, if I had something divided by 36, we can do the opposite of that. Times it by 36. That's the long way, okay? Because that's obviously going to cancel it out, isn't it? So we're looking at h is equal to, in your CAS calculator, which is 36 sine of 48 degrees, which is what, Guy? What did you get for that? 36.48 sine of 48. 26.75. 26.75. Now it says correct to 3 decimal places. So 26, can I have a look? 36, so 26.753. 753. Now be careful. Have we been asked for a particular height in centimeters or something? No, it doesn't seem like it. So we're going to stick with our meters, yeah? Be very careful because sometimes they can ask you 2 centimeters. Find the angle of the horizontal of the cable reaching from point B. So can you see there, I've got this angle in here which we don't know. I'm going to call it theta. You can call it alpha, beta, gamma, delta, whatever the hell you like it. Okay? But sure, use theta. And you know what? Let's draw another triangle just because we can. There's theta. And let's do, now we need to use this 26.753 and we've got 24 over here. Now, over here we've got the opposite to my angle theta and I've got my adjacent. We don't care what the hypotenuse is for the time being. So let's do that. We've got to do tan, don't we? TOA. SOHCAHTOA uses tan. But this time we've got tan of theta is equal to opposite, which is 26.753, over the adjacent, which is 24. And likewise, if we're doing this a long way, we'd have to do the inverse tan of both sides. Well, this is what we're doing, really. You don't need to show this working. I just think it's nice to know why on God's earth we do some things in maths. It's nice to know that's why, because the tan and the inverse tan are the inverse of each other. That means that that's going to cancel out, and we're left with theta is equal to that. Let's do that inside in my calculator, 26.753. We've got this, and hopefully you can do, so we go we go Trig. Let's try that again. We go Trig, and we're looking for tan of control divide 26.573. 753. And that's over 24. 48.104. We're looking for correct to 2 decimal places. So 48.1. We're looking at the third one. Is it 5 or more? Well, it's 5 or more, so we'd be rounding that up to 2 decimal places. Now, if you have a look, this is exactly the same sort of thing. You could try this one here in your notes and have a go, but we're out of time today. It's going to be very, very similar. I'll get you to try that. This one here, by the way, is in your exercise books, so you can check that out. That's about it.